I'll talk today about one more kind of way or scenario that may come up that you need to count, and then we'll move back into probability. All right. So if this were 233, we would do like the proof of the binomial theorem. We would do it through induction, but we're not going to do that in here, but we will state it and then catapult off of that to the multinomial coefficient. So perhaps, so we already know n choose k, what that means, right? That's a combination of n items taken k at a time, where repetition is not allowed. And order doesn't matter. So that is a combination, and we know how to calculate it. It's n factorial, n minus k factorial, right? That's n choose r, and this is actually called a binomial coefficient. And the reason we call it that is it does appear in our binomial theorem, which is, so let's write the binomial theorem down. So if you have x plus y to the nth power, you already know how to do this squared, right? You FOIL it and you get that x squared plus 2xy. Let's look at that. X plus y squared is x squared plus twice xy plus y squared. Does anybody know what x plus y cubed is off the top of their head? X cubed plus 3x squared y plus 3xy squared plus y cubed, I believe is correct. We'll verify it here in a minute. And obviously the fourth you could do, but it would take a long time. You got to multiply it out by hand. Okay, so what the binomial theorem says is that for any positive integer n, x plus y to the nth can be found by summing up. We're going to do k, starting at k equals 0 up to n. N choose k, there's our binomial coefficient. X to the k, y to the n minus k. Sorry, I'm going to move this down just a little bit so it doesn't cloud up my wisdom. Okay. Now let's verify it. Let's use the theorem on this one. By using the, we just FOILed that. We could do that in our sleep, but if we were wanting to use the binomial theorem, I'm going to do it here. It's saying sum up from k equals 0 up to 2. 2 choose k, so we'll run through that. Plus, oops, not plus, times, x to the k, y to the 2 minus k. Okay, so starting at 0, we get 2 choose 0, x to the 0, y to the 2 minus 0. Plus, now we move over to 1. 2 choose 1, x to the 1, y to the 2 minus 1, plus, lastly, 2 choose 2, x squared, y to the 2 minus 2. And if we clean that up a little, we know 2 choose 0 is 1, x to the 0 is 1, and this is just y squared. Plus 2 choose 2 is 2, x, y. Oh my gosh, it's working. And then 2 choose 2 is 1, x squared, y to the 0. It's in a different order, but it is still the same. Let's do the cubed. X plus y cubed would be summing up from k equals 0 up to 3. 3 choose k, x to the k, y to the 3 minus k. Or you could start the x's high. You could say x to the 3 minus k, y to the k, right? It doesn't matter. This addition is commutative across the reals. So what is this? Equals 3 choose 0, x to the 0, y to the third, plus 3 choose 1, x to the 1, y squared, plus 3 choose 2, x squared, y to the 1, plus 3 choose 3, x cubed, y to the 0. And again, that is y cubed plus 3xy squared plus 3x squared y plus x cubed. You could also get this by way of Pascal's triangle, but this is why we call this our n choose k which we know it as a combination of n distinct items taking k at a time as a binomial coefficient. Why we bring this up here, other than the fact that it's cool, is that we also want to be able to talk about a multinomial coefficient and how we can use that in counting as well. Okay, so we're going to talk about the multinomial coefficient. So tell me if you all know what I'm defining here, okay? So if you have a set of n distinct objects divided into r distinct groups, so no overlap, okay? I want you to think no overlap, with respective sizes n sub 1, n sub 2, all the way to n sub r, where if you summed up all of that, n1 plus n2 plus n sub r, you should get all the events n. So a set of n distinct objects divided into x, y, z, z is a what? Anybody? Of n objects into our groups. Anybody know what we're defining? If you've taken computer science, you should know. Yes, good. Partition. So a partition takes a set and divides it up into non-overlapping sets such that if you union up all those sets, you get the whole set again. So nothing is left out and nothing is counted in more than one group. So a good way to look at this is a picture, right? Picture lots of things inside your group. They're all different, and maybe you split them up into some bunch of sets, but you get them all, okay? That's a partition of these groups. I'm sorry, of these elements. And notice that I said are distinct groups. So that is an ordering, right? So the first group is different than the second group, which is different than the third group, and so forth. Okay, so let's count the number of ways to do that. How many partitions of n distinct objects divided into R groups with sizes n1, n2, n sub r. Okay, so let's systematically see if we can do that. We do care about the order, so we'll decide the first. So the first, by the way, the first group gets n sub 1 items. The second group gets n sub 2 items. The next one gets n sub 3 items, all the way down to however many is in the rth group. Okay, that's what we've decided. So the number of ways you can take the n things and pull off n1, where we don't care about the order once we're inside the set. We just care about that it's that in the first set. That make sense? Okay, well, at the next step, we don't have n objects anymore. We've pulled off n sub 1 of them. So of those remaining ones, we're going to pick the next amount that goes into the second group, right? What would be the third amount that we have left? What would be the next coefficient that goes there, or next factor that goes there? How many do we have left now? Yes, n minus n1 minus n2. I pulled off however many, and now I need to choose the amount that goes into the third. Good. And I knew what you meant. And then lastly, I should only have that many left and I choose them all. Well, let's actually figure out what the second to last group is, right? We will have, we will have pulled off everything up to nr minus 1. And we're going to choose nr minus 1. No, that's not right. Is that what I want to say? I'm going to leave that for a minute before I upset myself. We're going to go all the way down to the end, then we'll come back and figure it out. N choose R, N choose R. So we should have everything except, yeah, we should have it. We should have had what I had there, right? I think we should have. Okay, and we're like, let's see it with an example, and then maybe we can see what this thing reduces to. So let's say we have 26 letters of the alphabet. They're all distinct, you understand. And we want to partition those letters into the following groups of size 5, the next group 10, the next group 2, then 6, then 3. Okay, so following this logic, the first step is to find from the 26 letters, we'll choose groups of 5. We don't care about them once they're in that group, so we don't want to count for their order, right? After we've done that, we now only have 21 letters, or 26 minus 5, and we now need to choose the 10 that go in that group, right? At this stage, we now only have 11 letters because we've already pulled off 15 of them, and we need to choose 2 that go into that set. What's my next one?
9 and 6.
9 choose 6, and lastly, we better have 3 choose 3, and that is correct. Okay, so that should make sense. Let's see if this simplifies, because that seems like that's a lot of computation anyway, if I wanted to compute it. So let's write this out. So this really is 26 factorial over 5 factorial, and then 26 minus 5 factorial, right? Or 21 factorial. I'm going to write it as 21 factorial because it'll be easier for us to see. All right, the next one is 21 factorial over 10 factorial times 21 minus 10, or 11 factorial. The next step, 11 factorial, 2 factorial, 2 minus 11, or 9 factorial. 9 factorial, 6 factorial, 9 minus 6, or 3 factorial, 3 factorial over 3 factorial, 3 minus 3 factorial. And look at this beautifulness. So what we're really left with is just the 26 all over all the pieces. 5 factorial, 10 factorial, 2 factorial, 6 factorial, 3 factorial. Okay, let's see if that holds for our formula in general and if we can get there. Right, so that first one would be n factorial over n1 factorial, n minus n1 factorial. Right, the next one would be n minus n1 factorial over n2 factorial, and then n minus n1 minus n2 factorial. See what's happening? Times the next one would be n minus n1 minus n2. I feel like I'm writing too many of these out. So let's just do this and then we'll move forward. That's on top, n3 factorial, and then n minus n1 minus n2 minus n3 factorial. dot, dot, dot. Now we're going to do the last two terms. I'm going to do it this time. So now we have n minus n1 minus n2 minus dot, 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 minus, this is the second to last term, so it's going to be n sub r minus 1 factorial. This is going to be over n r minus 1 factorial, and then n minus n1 minus dot, 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 minus n r minus 1 minus n sub r factorial. Woo! Don't tune me out. And then the last term should be what? N r factorial over n r factorial, n r minus n r factorial. Actually, sorry, that's not true at all. It's this expression. N minus n1 minus n2 minus dot, 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 minus n sub r factorial. And look what happens. Beep. Boop. I feel like I've done something. I'll have to look. Beep, boop, beep, boop, beep, boop. That's the one there. Beep, boop. That's just 0. So what do we end up with? I need glasses again. I lose them constantly. And what do we have? We have n factorial over n1 factorial, n2 factorial, dot, 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 n sub r factorial. Similar to the binomial coefficient. Right. Multinomial coefficient.